So, hello, I'm Noelia Martinez. I'm a postdoc at the Australian National University, and I'm going to present the commissioning status of the Laser Guided Star facility that we are commissioning here at Mount Stromlo Observatory in the 1.8 meter telescope. So I'm going to keep everything really brief. Feel free to ask me questions later or send me an email or whatever you want. Here we have two adaptive optic systems that are not for astronomy. So they are for space situational awareness, which is basically tracking, characterizing, and maneuvering space debris. But basically the technology is the same. The first system that we have is called AOI, Adaptive Optics for Satellite and Debris Imaging. It was commissioned last year. It can get a resolution of 50 centimeters for objects at 800 kilometers range. And here what you can see is the commissioning results when imaging the Cosmos satellite. So we got an straight ratio of 27% in closed loop together with a lucky imaging stack of images. The second adaptive optics system is called AOTP, the Adaptive Optics for Tracking and Pushing of Space Debris. It's actually a demonstration instrument to prove the feasibility of perturbating the orbit of an object in low Earth orbit by applying photon pressure with a ground-based adaptive optics corrected high-power laser. So the adaptive optics system is going to pre-compensate the high-power laser that is going to apply the photon pressure on the debris target. In order to apply this pre-compensation, the adaptive optics system needs to measure the turbulence ahead of the target because we need to cope with the movement of the target across the sky. So for that, we have our laser guided star facility, and this is the architecture as Samia presented before. It's basically divided into three main subsystems: the beam combining optics, the beam transfer optics, and the laser launch telescope. Everything is installed at the dome of the EOS 1.8 meter telescope at Stromlo. Some part of the system is within an enclosure together with the lasers, and some other part is enclosed in the center section of the telescope, or the main telescope. If we look at the beam combining optics, this is the subsystem in where the ANU guided star laser is either single propagated or propagated in combination with the EOS laser. So here I summarize the main characteristics of both guided star lasers. So they are sodium guided star lasers. The EOS one is a sound frequency generation of 589 of those two wavelengths, and the ANU laser is a semiconductor guided star laser. Once we continue with this, the beam transfer optics inside the enclosure, so those transfer optics relay and expand the beam. So we have already integrated the system in the lab and in the telescope. So those are two images of the integration and alignment phases. About the beam transfer optics outside the laser guided star enclosure. These transfer optics relay the laser beam from the guided star laser enclosure through the window throughout the center section of the telescope and to the last subsystem, the laser launch telescope. This subsystem has also been integrated and aligned in the telescope. And then the last subsystem that we have is the laser launch telescope. So it's a reflective LLT. It has a clear aperture of 32 centimeters and a field of view of 137 arc seconds with a magnification factor of 20. The laser launch telescope has been fully built by the Australian National University. It's been aligned in the lab and integrated in the telescope, and also aligned with the optical axis of the main telescope, of the 1.8 meter telescope. And this is what we were doing at the beginning of March, so right before lockdown. So basically the current status of the facility is the following. So the EOS guided star laser has been integrated and aligned on the telescope, so it's ready to go. We have one sodium guided star laser ready to have the first light of the laser guided star facility. The ANU guided star laser is still being integrated in the lab because it has suffered a modification in the design based on some faults in the previous design. So it's still in the States, in the labs of RT Associates. It's the industry partner developing this laser together with the ANU. The beam combining optics and beam transfer optics have been integrated and aligned in the guided star laser enclosure and telescope center section. The laser launch telescope is integrated and aligned with the optical axis of the EOS 1.8 meter telescope. And the commissioning phase is in standby because the EOS telescope suffered a big maintenance and it was deeply affected by COVID-19. So there are still parts missing that need to arrive. So we are still waiting since March. So it's not clear when we are going to resume this activity, hopefully soon. But this is the actual state of the Laser Guided Star facility. So that's everything I have. Thank you for your attention and feel free to ask as many questions as you want.
Thank you. Very interesting talk. I'm just wondering if there are any questions on the Slack. So while people start thinking about the questions, I do have a question for you, and it's related actually to the altitude of the angular altitude of the laser. So if I understood correctly, what the idea in launching in changing the orbit of a debris is actually to slow it down. So to slow it down, you have to send the laser as low as possible in the horizon. On the other hand, this is where you have the largest turbulence effective, let's say, effective path. And so I'm just wondering if there is an optimal angular altitude, let's say, or zenithal distance, where, let's say, the control of the power of the laser is good enough, but on the other hand, the angle is not so bad that you can slow down the target.
So it's actually a matter of doing it several times. So just with one shot, we cannot slow down the piece of space debris because the power is not enough. Even if we are talking about 20 kilowatt laser, and with the adaptive optic systems, it will be pre-compensated. So focused as much as possible on the debris target, but it's not enough because we are talking about photon pressure and not ablation. So we are not destroying the target. We are just, applying a momentum transfer. So it needs several passes. So it is indeed needs to be closer to the horizon. Now I don't remember exactly the angle. I think it was around 30 something degrees. And it needs to be several times. So this is a system designed to prove the feasibility to use this technique in case of a collision avoidance. And right now, the prediction time of a collision is around 1.5 days. So between when a collision is predicted and when it's going to happen. So this is the time that we have to do as many passes as we can on the debris target to slightly move it out of the way.
Okay, thank you. And let's say at this altitude, the orbit is a few hours. So you have, let's say 10 or 10-ish, let's say shocks to it to move it out of the way. Okay, thanks a lot. We have to recover some time. So let's continue with our next speaker. Oh no, now we have a break, right? Or not? No, we do have a break in my schedule of 10 minutes, but because we are late by 6 minutes. I will just.
We are not, Paulo. So, sorry to jump in, because there's one less talk in this on the last slot, right? That was cancelled. Okay. So I think we're right on time. So we can enlarge the discussion or give some time to. There's a question by Domenico. As you're calling the strings.
I'm just wondering. Oh, there is a Domenico. Domenico, go ahead and ask your question. Thank you.
Hi everyone. Noelia, the question is related to the fact that, as you know, there is a foreseen increase of the number of satellites, which is really big. And we are discussing in astronomy as well if it's a problem. do you see the risk of shooting two targets at the same time? You know, when trying to get the debris, you could get something along the line of sight. Has this been looked at, or will be looked at?
Yes, so I don't know if it's going to be looked at, but you're absolutely right. With the increase of amount of things up there, that could happen, but I don't think they would be that close, because we are aiming at a resolution of hundreds of meters with this system. So I doubt it would be like two different objects, not part of the same object, right? Orbiting together closer than 100 meters.
Or not necessarily closer, just on the line of sight. So it could be that you're moving also the orbit of something which is farther out.
Well, it should be something actually closer, because farther out, I mean, it would barely reach. So if there is something closer in the line of sight, it might be, yeah, maybe happen. But I don't think it has been studied, actually. But it's a good point. Yeah, definitely.
I don't know if Robert is still watching the presentation, if he has a comment on this. Robert Johnson?
Yeah, so the question was whether or not you could accidentally hit the wrong satellite, I guess, or hit more than one. Yeah, when we have this process called laser clearinghouse, and all the US astronomers that use sodium beacons or Rayleigh beacons have to go through this process, and you make sure that, other than your intended target, there's nothing else even close. I think the keep out angle is like 3.5 degrees, half angle. So as long as you go through that process, it's not a problem. As far as pushing the debris into another orbit, well, that's a really serious problem, I think.
And also we are talking here about, launching a 20 kilowatt laser, right? So we need a lot of permissions and a lot of procedures to do that, because it's not just, okay, I'm just going to launch my 20 kilowatt laser up there. So we need to make sure nothing is in the way. So
yeah, as long as you go through this laser clearinghouse process, they'll let you know if anything's even close.
Exactly.
Yeah.
So Robert, you have, I heard also a discussion about this. You must have a discussion about this program from Amazon, from different groups to launch tens of thousands of satellites. So this will change the picture, I guess. Clearinghouse.
Yeah, we have a process where we look at each of the satellites and see how vulnerable they are to laser radiation. So, we can characterize them that way. And I think a lot of the CubeSats are not susceptible to laser radiation, at least not from sodium beacons. Maybe from a 20 kilowatt they would be, but not from a sodium beacon.